Hello, everybody. I am super excited to be here today to talk about contract inheritance in Solidity. We're going to learn how to resolve inheritance instances like contract A is contract B and contract C and so on. And then B inherits from D and so on. So all these complex inheritance structures we'll learn today. We'll learn how to deal with the so-called diamond problem as well. We'll learn how to do a rather complex problem as well of contract resolution. So why is that helpful? It's going to make you a better programmer, first of all. It's going to make you also understand when there are issues with contract inheritance, because sometimes it can actually error out. And then also it will just help you understand better, how to structure the inheritance, right? So when is what called? You want some function to be called, you're calling the keyword super dot some function and so on. Which function is called and why? It'll just help you better understand this inheritance structure and become a better programmer, as mentioned. So it's very important to really get a good grasp of. So today, when you leave this video, you will really grok what it means to inherit from a contract, what it means to do multiple inheritances and things like that. So I hope this video is going to be helpful. And if it is, if you don't mind supporting this channel, it'd be helpful. It does take a while to put these together. So like and subscribe. And I'm very happy to have you here. Let's get started. So, inheritance and Solidity. The way that inheritance works and gets resolved is via something called C3 linearization. This is just an algorithm. There could be other algorithms. This is just the way that Solidity has chosen to do it. If you look up C3 linearization, like I did here on Wikipedia, you'll get an explanation of what it is. And in essence, there's a quote here from Guido, who created Python. And he said, basically, the idea behind C3 is that if you write down all the ordering rules imposed by inheritance relationships, okay, so there's some rules on how to order things, in a complex class hierarchy, so we'll see one later, the algorithm will determine a monotonic ordering of the classes that satisfies all of them. So it'll kind of go from one to the other in a monotonic fashion. It won't circle around or anything like that. If such an ordering cannot be determined, the algorithm will fail. So that's the basics of C3. Okay, now we know that. That's fine, but how do we actually use it? I will make a note now that C3 linearization, as is apparent here, is implemented in Python. So Python follows that algorithm. So many of the examples we'll go through today are in Python, but they directly translate Solidity with one exception, and we will dive into what that exception is. We'll see what it is. So it is the same algorithm, but it's just the way that you choose the classes to include in your hierarchy. It'll get more specific later, is a little bit different in Solidity than it is in Python. But if we know how to do it in Python, we definitely know how to do it in Solidity, okay? So don't think that, we're doing it in Python now, that's not going to help me in Solidity. No, it is. The underlying algorithm is the same, which technically inherits from object. I haven't shown object over here, but this is how it looks. Okay, so I will never visualize object, but technically you can just imagine that being another class up here that is inherited from. So it looks like this. So there's a D class, there's a B class, there's an A class, and you can imagine where this inheritance resolution becomes important is if you have some sort of foo function or something like that in your D class, and maybe you want to call a super.foo, like which function do we call and so on. So that's where it's generally useful. And also just maybe in the case of Solidity, understanding the storage layout, right? Because as we start to inherit, those inherited contracts will start to take out storage and stuff, which certainly becomes relevant in the case of creating proxies, right? But is generally very useful to know. So you will understand why is contract A storage first and then B and then D and so on, right? Now in Solidity, it's just a little bit different, but very similar, right? We just write contract instead. We say A, we don't need an explicit pass or anything. We just do empty curly braces here. B is A, that's the syntax. So in Python, you just put the parenthesis. In Solidity, you say B is A to inherit, and then contract D is B, okay? That's the equivalent statement in Solidity, all right? So that's just going to be the notation. Again, we'll do a lot of the Python stuff, and we will highlight the difference between Python and Solidity. Just want to highlight this again, which we already did. There's a difference between Python and Solidity. We will talk about it. Now, when we talk about inheritance, the classical thing that always comes up is, the diamond problem. How are you going to resolve the diamond problem, okay? Because this up here is very easy. It's just a linear inheritance, right? And everybody's like, what's the big deal? Well, the big deal is when we run into the diamond problem. So it is even referred to as the deadly diamond of death. Okay, so it's pretty extreme. But the idea is you have an inheritance structure like this. And D inherits from both B and C, and B and C inherit from A. Okay, So in this case, the question is basically, okay, well, which contract comes next in the inheritance tree? How should we line it up? How should we order this, right? So that's what this algorithm, the C3 algorithm, that is what that can help resolve as well. It can handle these cases as well, and we'll see that. And you can actually look that up on Wikipedia too. This is a general algorithm for solving C3 linearization. Like this is the actual algorithm used in Solidity and in Python, except again, that one thing that we'll say in a second, but the algorithm is the same. So what do we do? We're going to introduce some new notation here. So some of the notation is this L, which is the linearization. Okay, L for linearization. And let's say we have some class C that depends on, or that inherits from class B1, B2, up to Bn. Okay, these are just some general labels. So it inherits, this class C inherits from these, and we want to linearize class C. In other words, what does linearization mean? It just means we want to write out the kind of the inheritance tree, so to speak. We want to say, okay, well, first C, and then B, and then D, and so on, right? That's the linearization. So that's the goal. And once we have the linearization, then we understand exactly how the class is kind of laid out, if you will. So the equivalent example in Solidity is if each class you inherit from takes, say, one storage slot, at the end of the day, you want to know the linearization so that you know in which order these storage slots will appear in your final, like, most base contract, like C, okay? So that's just one simple example. The other ones were the functions we talked about, which function exactly is called. Well, you need to know the linearization to do that. So linearization is the goal of this class, is called C here, okay? So how to do that? Well, the first thing you do in this algorithm is basically just, in general, when you see linearization of something that depends on something else, you just take the something, which in this case is C, right? That's the first thing. That's the thing we're trying to linearize. You can just extract that directly and say, well, the next thing that gets called is C in this linearization, right? Because that's the most parent class. All right, C. But then we do plus, and then we need to merge it with, like, we need to do a merge of all this stuff. So this is the merge operation. We'll talk about that right down here, but not right now. So just imagine there's a merge operation. We don't know what it is yet. And what does that do? Well, we need to now put the individual linearizations of these dependent classes here. So we put linearization of B1, notice the comma, linearization of B2, comma, and so on, comma, linearization of Bn up to Bn. So we put all these dependencies, all these derived classes as separate linearizations in this merge, comma, and then essentially all of them concatenated together, which in the notation over here is going to be as lists. They're going to talk about lists. I will also refer to this as a list. Would it be slightly more better to say something like this if I call it a list? Like comma, 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 comma? Yes, and that's what they do over there in the Wikipedia. But just for simplicity and notation, not write too many brackets, I will just call that a list. It's just a list of these classes, and they're just all kind of together. Like, meaning there is not a comma between them. You see, there's a comma between over here. There's not a comma between these. So this is a chunk of classes, right, or contracts in Solidity. All right, that's important. That's going to be important. We'll see how. Now, another thing we need to introduce in terms of concepts is there's going to be a head and a tail. So what that means is in this chunk here, B1 is the head. It's like the first. It's the most base class, the most parent class. That's the head, and then the tail is kind of everything else. Okay, so that will be B2, B3, Bn. Those will be tails. So that's all that means. It's just so we can talk about it a little bit more easily, and it will become later. It will become important later in the algorithm. Okay, so again, here's an example. Given B1, B2, B3, B1 is the head, B2 and B3 form the tail. Okay, and then another example is if you just see B2 by itself. Well, is it a head or a tail? Well, it's a head, and there's just no tail. All right, so just so we know that. Now, let's talk about the merge operation. So the merge operation basically means here, once you resolve this, notice the recursion here, by the way. I just want to highlight that. The linearization of C depends on the linearization of B1, of B2, and so on. But notice it's a smaller problem, right? Because you've taken out C, so you're not back at square one. You have reduced your problem size because you're linearizing a subset of this, right? Like, of whatever it depends on. And so you can imagine when you linearize B1, now you just need to go down and linearize whatever that depends on. So there's a whole recursive formula, as you can see. Anyway, so when you do the merge operation, what you want to do is, let's say you have resolved this, whatever it ends up being. Okay, so let's say if it's only B1, it'll just be B1. That's the linearization of B1, just B1. And in Python, we'll have B1O, where O is this object thing, because everything will always basically inherit from object. So we denote an O, but in Solidity, it would just be B1. But So you have B1, let's say B2 is just B2, Bn is Bn. The point is you have B1, comma B2, comma Bn, comma B1, B2, Bn. All right. In this case, the merge operation would, and we will see it in as an example later, take the head of the first list. So it would take B1, that's the first list, B1. And then if the head is not in the tail of any other list, add it to the linearization of C and remove all instances. Okay, so what that means is you take the head, which is B1, then you look for B1 in the tail of any of this stuff. Is B1 in the tail here? If this would just be B2, it wouldn't be, so no, and so on, right? And then over here, if B1 is first, that's the head, so it wouldn't be in the tail. So that's a valid head, and you can use that in your next recursion. All right, and we'll see the algorithm, don't worry, but that's kind of what the merge operation is. It starts to pick things, it starts to pick the next head to use in this linearization. So C will start as the first head here, right, in this linearization, plus merge, and then there's that recursion. And then the question is, what should be the next head? In other words, what should be the next class that comes after C, right, in this tree? Okay, that's what we're trying to pick, and that's what the merge operation helps us with. And we will see very specific examples of exactly how that is done, but just be aware of it. That is there. So that's a little bit of notation. In the C3 linearization in Wikipedia, which, by the way, we will do this very complicated example later, all right, step by step, which is also done here, but I just want to do it more visually, I suppose. But in here, they're using slightly different notation. This is kind of more pseudocode, but that's okay. It means all the same. They're also referring to this merge operation and all this stuff. And as I mentioned, they are actually putting formal lists around these things. I will avoid that just for notation and so on, like clarity and things. So we have a simple problem. We've already kind of seen this before. A inherits from B, inherits from C, and so on. So there's this chain. This is how you'd write it. A inherits from B, B inherits from C, and C inherits technically from object. It's not shown, but that's what it does. All right, very simple thing. Now, this is Python again, notation, but let's look at the algorithm. So what we want to do is we want to solve for the linearization of A. We want to figure out what's the storage layout in Solidity, or what would be the function that gets called if we call super dot whatever. Okay. So the linearization of A, again, according to the algorithm, we extract A immediately. That becomes the first class that's called. That makes sense. Plus merge, and then we have to put whatever it depends on recursively as linearization. So linearization of B doesn't depend on anything else. That's all we put. But then we need to put comma B. So we need to put the class itself here, not just the linearization, but the class itself. And that's it. Now there's a recursion. So we resolve what this merge is. All right. So to do that, we first need to resolve what L of B is. Well, L of B depends on C, right? Right here. We need to put B first. Great, we put B. Then we merge whatever that depends on, which is L of C and C. So you see how the problem keeps getting smaller, but it is recursion. So now we need to resolve L of C. Great, let's do L of C. L of C, again, doesn't really depend on anything. Technically object, so we could have put that here, right? So we could have put, again, this is just more for Python, but we could have put object here. Or we will just say when object, we just say O, okay? O for object. So technically, this is how it looks, L of O, L of C of O. We extract C, now we merge with L of O, O. So we have another recursion, but now we're at the top, we're at the end of the recursion. O is the final thing, great. Let's linearize O. Linearizing O is just linearizing this like object, the most kind of derived class in Python thing. So it's just everybody inherits from it. But that is just O itself, okay? That's just kind of a fact. It says that up here too in the Wikipedia here. This is just the L of O, the linearization of O is just O. The linearization of O is trivially the singleton list O, because O has no parents, okay? O has no parents at all. So that's just O. Just again, this is more Python thing, but just be aware of it. So merge O of O, well, that just gives you O, because you pick, what's the algorithm? You pick the first head that you can, that's O. Is O in any tail in the remaining lists? Nope, O is a head here, it's not in the tail, and there's no more lists. So great, O is a good valid head to pick. Great, CO. Okay, so that's LCO. Now we have that, we can start going back up the recursion tree, right? Because now we're at the bottom here, we can start inserting that here and then fulfill this, kind of like solve for this. Then when we have that result, we'll put that in here and solve for this. So it's kind of like, we recurse down and then recurse back up, standard recursion. So now we come back here, we're going to insert now L of BC. L of BC is here. It's B plus the merge here, which is B plus the merge. We're going to insert L of CO. L of CO, we figured out was CO. Okay, I'm going to move my picture around with the finger pointing here. So CO is we're going to insert here, which was what we needed here. All right, so this is this result. So that's why that sits here. Okay, so B plus merge CO with C. Great. Let's pick a head from this list. That's the merge operation. We need to pick a head, a candidate first. Let's see. C is the first head we see in all the lists in the merge, right? C, because C is the head, O is the tail. So C is the first head candidate. I say candidate because what if C appears in a tail later on? Then it's not a valid head to pick now. Now, it happens to be that C is a head candidate. We check over here. Is C a tail? No, C is not in the tail. Great. That's good. C, we can pick. So we're going to pick C, B plus C. The kind of plus here is meaning kind of merge it together or start creating a list. So, and we'll see what that means. So B plus C, fantastic. We found it. Now remove C from all the lists here. There are only 2 lists. Remove C from here. Remove C from here. What's left? Just O, because this becomes empty, so we don't say that. So we just merge with O. Merge of O is very trivial. It's just O, okay? Because you pick the head O. You check if O is an other tail. Well, there is no other list to check in, so it's valid automatically. So this becomes BCO, the list BCO, all right? And again, in that Wikipedia article, the notation they're using is B, comma, C, comma, when they call that a list, right? So that makes more sense to call it a list, okay? That's what the result would be, according to that Wikipedia and their notation. I'm just going to write it like this, BCO, okay? Great. Now we have L of BC. Great, that's fantastic. We have this result right here, which we can insert right here to find finally L of A. So we keep going. So L of A is now A, we extract A plus we merge. BCO is just this result we insert, comma B. Fantastic. Let's pick a head candidate. So we're going to pick B because that's the first head we see, B. Now we're going to go check the other lists. Is B a tail? Here? No, B is a head here. There's no tail. It's just a head. Great, that's valid. So B is a valid head. Extracted, AB. I'm not going to put the plus this time, so just AB. Okay. Plus, merge, and we're going to remove B from here. We're going to remove B from here. We're going to have to do it for all lists. There's only 2. So all that remains is CO, because this becomes empty. So CO. Great. Is C, pick C as a head candidate, is a valid head? Yeah, it is, because it's not in the tail of anything else. And so on. And then you keep doing it with O. Is O a valid head? Yes, it's not in the tail. So you can kind of see how it will speed things up a little bit, right? So A, B, C, O. Okay. So that is it. That's the result. So when you call A, right, like its hierarchy will be A, B, C, and then technically the object that we're not showing, which makes sense. This was a simple case. We didn't really need this algorithm for this case, right? Because that's pretty clear. There's no issues here with resolving anything, right? You would go from A to B to C, rather straightforward, but you get a little sense of the algorithm. We're going to do more complicated things. Great. So let's consider a less simple problem. Well, we're going to learn to handle the diamond problem now. That's exciting. So in Solidity, if you ever see the diamond inheritance problem and you're having some issues with it, well, now you know how to resolve it after this example. So again, this time, we have A again, but this time it inherits from B and C, and each of these inherit from D. So the question is kind of like, how do you get to D first? Like, what is do we go A, B, D, C, or do we go A, B, C, D, or do we go A, C, B, D, and so on, right? There are many paths here, but the C3 linearization will consistently give us the right ordering, or a ordering that is right according to C3. So anyway, the notation is like this in Python, right? Again, in Solidity, this would be a little different. We'll touch on that in a second. So class A inherits from B and C, B, C, right? And B inherits from D, C inherits from D, D inherits from object, and so on. Same thing as before, same notation as before. All right, let's get to it. So what's the solution? Well, we want this L of A, B, C. That's what we want. That is, just like before, we can extract A immediately, the most parent class, boom. Plus, and then we need the merge operation. It's a recursive again, so we need L of B, L of C, BC, the list BC, all right? That's what we need. So as you can probably tell now, you were probably Jesper, I can kind of see the structure now. We probably just need to go to the most derived class here and kind of work backwards almost. And I would agree, it's actually easier at this point. Now, certainly write down the start problem, this is what we want. But as you can see, now when we start to linearize B, well, we're probably going to get something where we need to linearize D and so on, right? So having L of D would be helpful at this point because we can plot that right into L of B and right into L of C, right? So you can kind of think about it like try to go to the most derived and kind of work backwards is generally helpful. So in this case, though, we will work forward, but I'm just saying in a later example that's very, very much more complicated, we'll do the opposite, okay? But let's just see how it looks working forward again. So we need L of B because it says it right here. B depends on D. We can extract B. That's always a valid head immediately because we just know that because that's the class we want to linearize. So of course the class itself is the most parent. So we do B plus merge, and then we just put linearization of whatever it depends on, L of D, D. So now we need L of D, right? But L of D, as we can see, I think we don't even need to do it, is obviously just D, right? Like L of D, you're going to write as D plus merge O, right? And merge O is just O, so it's just DO, right? So that's why it's D, and then the O comes in, okay? And this D won't even play an effect because this will be DO, this will be D, we pick D as head, and so on, and then the O will automatically come out anyway as the next valid head. Okay? To understand that, well, we just did the example, simple example above. So I'm going to take some shortcuts here and there, okay? So L of C looks very, very similar. It's just C plus, I mean, it's very, very identical to B. You just merge L of D again. You see this looks exactly the same. It's just going to be CDO. So there's no surprise there. All right? Now we have L of B, we have L of C. We are good to go because we need them right here. So what we're going to do is going to insert them up there. So we're going to have A plus merge BDO, CDO. Okay? BDO, CDO right here, comma BC. So we're going to pick the next available head or head candidate. So we pick B. Is B a valid head? Well, let's go over and see here. Is B in the tail? The tail is DO. Is B here? No. Is B here in the tail? No. B is the head here. That's fine. B is not in the tail. So B is actually valid. So we're going to extract that AB. So the next class after A is actually B, okay, in Python. So now we're going to say AB. Now we're going to recursively merge again. We're going to remove B from all instances. So no B is here, B is here. We're going to remove it here. We're going to remove it here. So we're going to keep merging. So now we have whatever remains, which is DO, CDO, and C. We're going to pick a head candidate. This becomes interesting now. We're going to pick D. Is D the next thing? So does it go A, B, D? Let's see. Pick D as a head candidate. Is D in the tail here? Ah, yes, it is in the tail. So that's not a valid candidate. We can't use that as the next head. The order is not A, B, D. All right? So what do we do then? Well, we just say, okay, that was not a valid head candidate. We'll go to the next potential candidate, which would be C in this case, because that's different than D, right? So C would be the next candidate. Is this a valid? Well, it's not in the tail over here, and it's not in the tail over here because C is the head. So that's great. C is a candidate. So we do A, B, C. So the order is more like A, B, C goes next, okay? And then we remove it from all the occurrences, which is here and here. So we remove it, and then we merge DO, DO. Well, now we pick D as a head candidate. Is D in the tail here? No, it is not. It is the head. It's not the tail. A, B, C, D plus merge OO, which is O, A, B, C, D, O. So the order is A, B, C, D, and then technically O in Python. Okay? That's how to do it. We solved the diamond problem. So it's not that scary. And then this just duplicate it. Okay. At this point, I want to stop because now it actually becomes relevant what happens in Solidity. So far, we looked at Python. The exception is that Solidity swaps the order that you put this in. So remember when we said A, B, C, right, to write this down? To do the equivalent of Solidity, the solution is not this. You would think that, you have A, B, C. You just write contract A is BC, right? And then all the rest is the same. No, that's not right. A is BC. The way the Solidity reads these inherited classes, so to speak, when it does the C3 linearization, is actually in reverse order than Python. Okay? So in Solidity, the order of the derived contracts are read right to left. So this is the most derived, this is the least derived, which I think kind of makes sense, actually, because this is more like the parent, like more closer to the parent. So that's kind of how it's read. In Python, it's read opposite, right? It's saying this is the most derived, this is the most base, all right? So it's exactly opposite, but the rest of the algorithm is the same. So as long as you just line it up in that new way. So what I mean by that is if we were to do the exact same algorithm up here, but with Solidity, we would just swap C and B in this order. You might be like, that doesn't matter. Yes, it does, because now you're going to linearize C first and then B here, okay? And that will affect the way in which you pick the first head candidate. Right? Remember, we picked B as the first one. We would have picked C if we swapped these two, and they would have swapped around. But the result is then going to be the same as long as you swap these two, because the order is different. Okay? That's the only difference there is between the two, but it's very important that you understand this difference. Okay? So this would actually be the equivalent setup in Solidity. Okay? That you do A is CB. This will generate the same as the Python one here, A of BC. Other than that, it's the same. Okay? So it also says that in the Solidity docs, by the way. You can go right now to the Solidity documentation and you will see this section that I highlighted right here. It says, especially the order in which the base classes are given in the is directive is important. You have to list the direct base contracts in the order from most base-like to most derived. Okay? Note that this order is the reverse of the one used in Python. That's the important thing. It is reversed compared to the one used in Python. So, that's just what it is. So you can see here that, the given bases are searched from right to left and in Solidity, and then left to right in Python. okay, in a depth first manner. That's it. That's the only catch between linearization. The algorithm is the same, so we might jump back to Python here for these other examples, but just be aware that the way that you would structure things would be opposite. So in this case, this is the Python equivalent, or this is the Python version of some class setup. Again, in Solidity, you would reverse these two, you would reverse these two, reverse these two to get the equivalent inheritance in Solidity, okay? Now, this is a more complex problem we're going to consider now. We did the diamond last. Now we're going to do A, C, B, and you can see they have like multiple inheritance like that. So it's going to get a little bit more complicated, but we're going to do the same. We're going to do L of A. A depends on B and C, okay? B and C in this order, which we just picked. That's just what the application called for. There's no rule to picking this order, except it just needs to make sense in your application, of course, right? Like that's not something that's like, oh, you should always put B first and then C. No, that's just an example. Just make that clear, right? This just depends on what you actually want to inherit from and in which order, right? So this is just something that's given to us. Consider this just given to us. It's B and C. Now we put A plus, and then we merge the rest. So we put L of B, L of C, you get it now, and then BC. I think we're pros of that. The question is now we need what is L of B, what is L of C, and so on. So you can see the recursion happens again. Well, L of C is going to depend on L of E, L of D. L of B is going to depend on F and D and so on, right? So you get it. So yeah, we need to recursively compute these L's because you see that L of C, which depends on D and E in that order, which is again just given by the application. That's not something that we decide or anything, or the algorithm decides. This is given to us. Is again, you can always do C plus merge L of D, L of E. We also have L of D, L of F. So we need all those done. So what is L of D? Well, L of D is just D plus merge L of object. Object, we've done this before. It's just going to be DO. That's pretty straightforward. L of E, again, you know when it's like a very derived class like that and there's nothing else it depends on, it's pretty straightforward. L of E is just EO. In Python, this O shows up in Solidity wouldn't. And then L of F is just FO. That's pretty straightforward. So again, you can when you see a tree, linearization tree in your head, you can just like linearize these immediately and say that's FO, EO, DO, right? And then you can start linearizing these. So let's do that. So for example, for B, well, we just insert the D and F, right? L of D, L of F, and then DF. And this should technically be, sorry, there's a typo there. So it can be like that, all right? DF. And then, so it's B plus this, okay? So B plus merge, and then this is DO. We'd know that immediately. It is FO, and this is DF. So you can even start now to become a little bit quicker in your mind too. When you see a structure like that, you can kind of see, well, this is FO, this is EO, DO. C is going to be C plus, EO, DO, right? I mean, DO, EO, because that's the order over here. So you can kind of see, okay, well, I know I'm going to get something C, and then D is going to be a valid class, like a valid head, right? So you can kind of see it becomes CDO, right? Kind of thing. So as you become better and better and you practice more and more, my point is just that you can almost do this in your head, right? You don't really need to write this down. But anyway, so let's do this. So B plus merge DO FO DF. Is D a valid head? Yes, it is. DO. D is not in the tail of anything else. It is in the head here, but not in the tail. Great. And this is actually a little bit better. You can pause the video too, but this is this is another description of the merge algorithm. But we're already experts at that. So you extract D as a valid head, you get BD right here. You merge it with, you remove D from all this. So you merge it with O, you merge it with FO and F. Fantastic. O, is that a valid head? No, it's in the tail here. So the next thing is not O. So we've got BD. Is F a valid head? Yeah, it's not in the tail here, it's not in the tail here. F is a valid head. So it's going to be BDF, okay? And then we're going to merge OO. We know that's just O. So BDFO, that's the order, okay? That's the order of B. So B goes B, D, F, and then technically O, all right? Now we're going to go next, though. We're going to do C. C is going to be very, very similar. We're going to expand C. We already know D, DO, EO. It's going to be D. Fantastic. We're going to pick D as a head candidate. Is it valid? Yes, it's not in the tail of the others, so it becomes CD. Is O a valid head? No, it's not. Is in the tail here. Is E? Yes, it is. CDE. O. That's it. CDO. Done. Now the final result is going to be, let's do it one line at a time. It's got to be A, B, C. Is B and C. Well, we just did C and we did B above. Let's insert them here. Boom. BDFO, CDEO. Great. Now we need to pick a head candidate. Let's pick B, right? Because that's the first list in the merge. B. Is it in the tail here? No, it's not. Is it in the tail here? No, it's not. B is good. Look at that. Remove it now from these lists. It's removed here and here. Next, potential head, next head candidate, D. Is D in the tail here? Yes, it is. It's not a valid head candidate. Okay, go to the next list. Is C in the head in the tail here? No, it's not. I'm picking C. Is it in the tail here? No, it's not. That's the head. Great. That's good. A, B, C. Now, remove C from all the instances here, which leaves this empty, and this is going to get removed. Let's pick D now. Now we can pick D, because now D is a candidate. We always start from the first list here. It's in the tail here. It is not anymore. Let's go. A, B, C, D. Now we merge. We remove the D from the others. We do F, O, E, O. F is the next, as you can tell. It's not in the tail over here. F is next. Great. O is in the tail here, so that's not a valid head. So E will become next. Done. A, B, C, D, F, E, O. That is the linearization. Boom. That is the answer. So now you know exactly how this complicated structure is resolved. And if you practice more and more, you will be able to do that in your head. So that is the structure. So let's take a look at it again here. If we move this up here, the inheritance structure and the way that, storage would be laid out, the way that functions would be called is A, B, C, D gets called next, F, E. Okay? That's not obvious if you just look at it. But now with the algorithm, you might be able to do it mentally as well. Let's look at a case where there is an invalid inheritance. I created a case here where you have F, like that F derives from D and E, and each of them, D wants B to be first, and then C. E wants C to be first, and then B. So here, you're going to hit a snack where it can't, each of these parent classes D and E, or more parent-ish classes D and E, will want the next child to be a different child. Like one is like, I want B to be next, I need C to be next. So that layer kind of can't be completed. You can't go to the next layer, to this yellow layer, because one wants B, the other wants C. So that's going to be a mess. But let's actually do this ourselves. See, and I'm going to show you the error in Solidity in a second, what it shows you. But here we get an error. You see this? Because this cannot be resolved. So Solidity will tell you the inheritance tree cannot be resolved, and we will learn how to compute why. We got L of F. F is the most parent class. It depends on D and E. Fantastic. We do the usual thing. F, and then we're going to merge D and E. Okay, great. We're going to go down here. We need to resolve L of D. L of D is right here, depends on B and C. Fantastic. D is the first valid hit. Merge the rest. We all know how this goes. Now we also need E, of course. We write up E, same thing. Now we need B, C, right, to resolve these two layers. Great. B and C, well, those depend on A, each of them. L of B of A, that's B plus merge L of A, A. We know what A is. A is AO, right? So this will become BA, technically with an O. Okay, I didn't write it here because this is more of a Solidity example here. But there's BA. And then CA is CA. Okay, those are simple because they're kind of like the BACA. That's pretty straightforward, right? Now we got those. We start walking back up the recursion chain. So we go L of E, which has C and B. Well, C and B, you just insert CA, BA, CB, right? Now, what is the next available, next valid head? We pick C. C is not in the tail of everything, so it becomes C. Boom. We remove C. A, nope, that's not a good next head because it's in the tail. So we have to pick B. E, C, B. Fantastic. Now we're left with A and we're good. E, C, B, A. That is what that is. Now we do D instead, okay? So D, same thing. Pick B. Yeah, we can pick B because it's not in the tail. Fantastic. Remove it. Go over here. Is A good? No, it's not. We need C and then we need A. D, B, C, A. Pretty straightforward. Great. Now we have those. We now walk up the recursion tree again to F. F is the ultimate class we want. Remember, F is up here. So D, E. We insert the linearizations of D and E right here. So D, B, C, A, that is this one, and E, C, B, A, that is that one for E. So is D a good head? Yep, because it's not in the tail of everything. Let's do it. Merge, remove the D from the other lists. Pick B. Is B a valid head? No, it's not, because in the tail over here, we can't do it. All right, go over here. Is E a valid head? Yeah, it is. It's in the, so far so good. So we have FD. Now remove E from the others, and then pick B as a potential valid head. Is B a good candidate? No, it's in the tail. Okay, no problem. Let's go to the next one. Is C a potential candidate for a head? No, because it's in the tail of this one. So you see now we're in a problem. We can't pick this as a valid head because it's over here. We can't pick this as a valid head because it's in the tail of over here. So we are stuck. That's it. We're stuck. So an exception is going to be thrown. We can't proceed. And now you know why. And that's why we're going to have an error. And I'll show you in Solidity what that error looks like right now. So we're gonna actually look at invalid here. Okay. So this is the contract right here. written out here. So we have F is DE, E is CB, and so on. But because of this switching here, we're going to get an error. So let's uncomment this and compile it. And look at that. It's going to say linearization of inheritance graph impossible. And now we know why. So it's going to throw an error because of this. Throws an exception because of this. That's what we're seeing here. So now we know. Now, if we were to change this to CB, for example, again, you would have to see if that could make sense in your application. Maybe sometimes that's okay to switch. Maybe sometimes it's not okay to switch. And then you have to kind of redesign the inheritance. Okay? Then that can work or not. So this does work because we switched. Another thing, since we have Solidity up now, is I want to show you, I wrote an example, and it's going to be in my repo here, so feel free to use it for anything you want. But basically, this is a way to actually print the inheritance tree of a Solidity contract. So we have something where A is CB, B is D, C is D, and then we have D. Okay, so we have some kind of like A is C and B, and then they go to D. So it's kind of like a diamond. So in this case, the way I just kind of implemented this was in the most derived contract D, I just have this dynamically changing inheritance path, and I will just use each constructor to push my name, like the name of this contract D here, C here, and so on, to this inheritance path. And then at the end, in the most base class, the most parent class, I have this function called getMRO, which is basically this resolution, right, of the path. That's the linearization, essentially, right? So basically, you can click that and you can get the path. All right. So what we're going to do is we're going to deploy this, and we're going to say get MRO. All right. And so you can see here in this case, right? So A, C, B, blah, blah. You can see the path gets printed right here as a string. So this is what's being put together from all the constructors, and it says A, B, C, D. Okay. So that's it. A, B, C, D. That's the path. So if you were to change something like this to this, so again, A, B, C, D. So let's deploy it again. Now it's A, C, B, D, because we swap these two, right? So anyway, just a small code to do that, to print that path for you, if you're ever curious. I'm sure there are other tools that can do that as well, but I just want to do something quick in Remix to do it. But that's kind of how you can get to understand that as well. But now you don't really need that because you have this algorithm, so you kind of know it. Okay, let's end off with the very complex example from the wiki page. Okay, but we're experts now, so we don't care. But the wiki page was this example right here. All right. Okay, that's this example right here. So you have some class Z, which is the one we're interested in, and that extends, or in Solidity, you would say like contract Z is, and then you would in Solidity do K1, K3, K2. In Python, you would then have to revert those depending on which order you actually want. But anyway, so Z here, as you can see, this is a whole tree. There's a whole tree of classes and contracts. So Z actually extends, or like is K1, is K3, is K2, K1 is C, blah, blah, blah. And then it all goes to O, which again, in Solidity has a little bit less meaning, but in Python certainly does. So in this case, we are plotting O just to follow this example over here. So let's look at it. How are we going to resolve it? L of Z depends on K1, K3, K2. We're going to do the usual stuff. We're going to extract Z. That's a valid head for sure. We always have that plus then we're going to start merging. But in this case, as I said earlier, we're going to start from the end and work backwards. So it's actually easier. So we're just going to start. So what I mean is we're going to start from the most derived classes here. So essentially, of course, O is just going to be O. And then C is going to be CO, AO, BO, DO, EO. We already know that. We can just read that right off. We don't need that special merge algorithm, all this kind of stuff, because it only depends on O, right? Each of them. There's no complication there. So this is just the result. We just write that. We just read that right off. All right. Now we can go up one layer, so to speak. But again, notice we're working backwards. We're starting here. Now we're going up to the yellow layer, K1. K1 depends on A and C. So K1 depends on C, O and B, sorry. So it's CAB. Great. So now we need to merge LC, LA, LB. Well, we all have that from up here. That's why it's helpful, right? And then CAB. So we're going to do K1 plus merge. We're just going to insert those linearizations, which is straight up CO, AO, BO, done, and then CAB. Is C a valid head? C is not in the tail anywhere. Yes, it is. Done. Remove it. What next? O, no, it's not good. A, yep, it's not in the tail. Let's do it and remove it. O, still not good. B, yes, and so on. K1, CA, BO. That's it. Pretty easy, right? Now we're experts. K3, same thing. I'm not going to cover that. You just insert the linearizations from before, because that's the same layer here. Those are straightforward. You do the merge algorithm. K3 ADO is the answer. K2 gives you K2 BDEO. Very complex example, but look at that. We're taking it one step at a time, and now we have the entire yellow layer resolved, which means we can do the blue layer or the final layer. So, C, we insert the linearization of K1, which is K1 CABO, right there. We insert K3, which is K3 ADO, right there. I actually did this in opposite order. That's good. Catch that. There we go. And then do K2. Insert K2, linearization of K2, which is this one. I think it turns out the result will be the same. But anyway, it's important to get that order right. And then, of course, put it in K1, K3, K2. K1, K3, K2. All right? So we got it here. Now we just need to start walking through these lists. So pick K1 as a potential head candidate. Is K1 in the tail? It is not. So it is a valid candidate. We get ZK1. Now we're going to remove it from all instances, and we're going to pick C. Is C a potential candidate here? It is not in the tail here, not in the tail. Yes, it is. So Z, K1, C. We're going to remove C from everywhere. Is A a valid head? No, it is not. Why? It's in the head. Is in the tail here. Not good. Go to K2. Is K2 a valid head? Nope. It's in the tail here. That's not good. Is K3 a valid head? Yes, it is. It's not in the tail here, not in the tail here, and not in the tail here. So we're going to get K3. Look at that. K3. Now we're going to remove K3 from everywhere. Now we're going to pick A. A, is it in the tail? Nope. Now A is valid. So let's pick A. Look at that. We picked A. Remove A from everywhere. What about B? No, B is not good. It's in the tail here. Great. What about K2? K2 is good because it's not in the tail here. Great. And then also now we're going to remove K2, and then we got B. Finally B. B is fine now because it's not in the tail anywhere. Great. Done. So that's B. You see? Picked it. Got to remove it. Is it O? Nope. O is in the tail here. Is it D? Yeah. Looks like a good candidate. Got to pick D. Remove D. O. Still no O. E. Yes. E. And then O, of course, at the end. That's it. That's a result right there. That very complex pattern above, this is the resolution. The MRO is the method resolution order that we saw before. That was what I called in Solidity, MRO, right? Method resolution order. But that just means the linearization of this, right? And in the wiki article, in this example that they're giving is, again, they would write it more as a list like this. And it might also be a little easier just because we've got these numbers 3 and 2 in there. It might look a little confusing. But if you just think of it as a list like this, then they each have a separate space there. Okay? So that's how it would be called. That's how the storage would be laid out, et cetera, in Solidity. Given that these would be contracts. You would put contract and is, all right? Sweet. That's it. We're at the end. Thanks for watching. I really hope that you understand in depth the Solidity linearization, which also happens to be the same as Python, except that the order of those derived classes are swapped. But other than that, the algorithm is there. We did a simple example. We did the diamond problem, which is a very famous inheritance problem. So we know how to solve that. We did a very complex example. We looked at also what it looks like when the inheritance path is invalid and why that happens. Now you will be able to go look at any contract and be able to understand the inheritance. Practice the algorithm a little bit, and certainly for easier inheritance paths, you will immediately be able to mentally derive the path. You don't need the whole algorithm. For way more complicated things, now you can just put it down on paper, and at least you have it available. Also, take a look at that code I wrote, implement it in your own graph, just to kind of double check your inheritance and your understanding, use it as an educational tool, whatever you want. And then finally, go like and subscribe to the channel if you like the content. We're going to dive in a lot more Ethereum and Solidity based learnings and potentially even expand further as we go along. But I just want to make sure the base fundamental understanding is super set. That's the only way you can become a fantastic engineer and go do great things. So thank you very much for watching. I appreciate you and the time here.